Welcome! In this session, we'll tackle LeetCode problem number 1119, titled Remove Vowels from a String. This is a beginner-friendly problem that focuses on string manipulation and filtering. We'll explore a simple and effective way to remove vowels from a given input string. Let's dive in. In this problem, we are tasked with removing all vowels from a given string S. The vowels we need to consider are a, E, I, O, and U. Once all vowels are removed, we return the resulting string. The input string S will only consist of lowercase English letters, and its length can range from 1 to 100,000 characters. For the output, we simply return the transformed string where no vowels remain. Let's look at an example to better understand the problem. If the input string is LeetCode isocommunity of forecoders, the vowels in this string are E, O, I, O, U, and E. Once we remove all these vowels, the resulting string becomes LTCDSCMMNTYFRCDRS. This example highlights how we process each character, keeping only the consonants and discarding the vowels. Now, consider another example where the input string is a EIOU. Since this string consists entirely of vowels, removing all vowels leaves us with an empty string. This demonstrates that if all characters in the string are vowels, the output will simply be an empty string. For a more general case, let's look at the string programming. Here, the vowels are O and A. After removing these vowels, the resulting string becomes PRGRMMNG. This shows how we skip vowels while constructing the output, ensuring that only consonants are included in the final result. Finally, let's go over some constraints and edge cases to keep in mind. The length of the input string S will always be between 1 and 100,000 characters, and the string will consist of only lowercase English letters. It's important to handle edge cases such as input strings that contain only vowels, which should result in an empty string, or strings that contain no vowels, where the output should match the input exactly. Additionally, for single character strings, we simply check if the character is a vowel or a consonant and return the appropriate result. Since the input size can be very large, it's crucial to implement a solution that is efficient in both time and space, ensuring it can handle the upper limit of 100,000 characters without performance issues. To solve the problem of removing vowels from a string, we can consider three main approaches. The first is the brute force approach. Here, the idea is simple: iterate through the string character by character, and construct a new string by appending only those characters that are not vowels. We can do this by checking each character against a set of vowels using a loop. While this method has a time complexity of O(n), which is optimal for a single pass through the string, it constructs the result string step by step, which can be inefficient due to Python's string immutability. Next, we have the optimized approach using list comprehension, which is a Python-specific technique. In this method, instead of appending characters to a string one by one, we collect non-vowel characters in a list and then join them into a single string at the end. This avoids the overhead of repeated string concatenation and is faster in Python. The time complexity remains O(n), and the space complexity is also O(n), since we use an intermediate list. Lastly, we have the approach using regular expressions. This method leverages Python's regex library to replace all vowels with an empty string. While concise and elegant, this technique can add unnecessary computational overhead due to the cost of using regex for such a simple task. All three approaches share the same time complexity of O(n) and space complexity of O(n), but there are trade-offs in terms of efficiency and readability. After evaluating the three approaches, we chose the optimized approach using list comprehension as our strategy. This decision was based on several factors. First, in terms of efficiency, list comprehension avoids the cost of repeated string concatenation by storing non-vowel characters in a list and using the join method to create the result string. This makes it faster than the brute force method, especially for longer strings. Second, the readability of this approach is a significant advantage. The use of list comprehension makes the solution concise and Pythonic, which is ideal when writing clean and maintainable code. Finally, the performance of this method is strong. With a time complexity of O(n) and a space complexity of O(n), it achieves the optimal balance for this task. Additionally, it's worth noting that checking membership in a set, such as the set of vowels, is an O(1) operation, which contributes to the overall efficiency. By contrast, regular expressions, while concise, introduce unnecessary computational overhead for such a straightforward problem, and the brute force approach, though functional, does not offer the same level of performance or simplicity. Regular expressions, though concise, can be overkill for a task as simple as removing vowels, introducing computational overhead that is unnecessary for this problem. The brute force approach, while straightforward and functional, is less efficient than the list comprehension method due to the costs associated with string concatenation in Python. The key insight or aha moment here is understanding the impact of Python's string immutability. Repeated concatenation in a loop creates new string objects each time, which is expensive. By using a list to collect characters first and then joining them into a final string, we avoid this inefficiency entirely. The final implementation of our chosen approach is clean, efficient, and leverages Python's strengths. By defining a set of vowels and using a list comprehension to filter out any character that is not a vowel, we achieve the desired result in an elegant one-liner. This solution ensures optimal performance while remaining easy to understand. Here's the Python code. Define a set of vowels, use a list comprehension to filter out vowels from the input string, and finally return the joined result. This approach achieves the goal of removing vowels in a fast, Pythonic, and readable way. To begin, the task is to remove all vowels from a given string, including both uppercase and lowercase vowels. For example, if the input is a string like hello, the output should be hill, since the vowels e and o are removed. To achieve this, we first identify the key operations. We need to go through each character in the string, check if it is a vowel, and, if not, append it to our result. The steps are straightforward. First, we initialize an empty list called result to store the characters that are not vowels. Using a list for this purpose is crucial because appending to a list is more efficient than directly concatenating strings, which can be costly in terms of memory and performance. Next, we define a set of vowels containing both uppercase and lowercase variants, such as a, e, and so on. Sets are particularly useful here because they allow for quick constant time lookup. Finally, we iterate through each character in the string, check if it belongs to the vowel set, and if not, we add it to our result list. These are the foundational steps of our algorithm. Once the iteration is complete, we move to the final step of the process. All the non-vowel characters collected in the result list are joined together to form the final output string. This string is then returned as the result. A critical part of this algorithm is handling edge cases effectively. For instance, if the input string is empty, we should simply return an empty string. If the string contains only vowels, we return an empty string as well, since no characters remain after removing vowels. On the other hand, if the string contains no vowels at all, the algorithm should return the string unchanged. Additionally, the algorithm is designed to handle mixed-case strings and non-alphabetic characters, like numbers or symbols, by ensuring that only vowels are removed. This approach is not only efficient but also scalable. Using a set for vowels ensures rapid membership checks, and building the result with a list avoids the inefficiencies of repeated string concatenation. The entire process operates with a linear time complexity, making it suitable for strings of any length. The algorithm is also robust due to its normalization of vowels into a single set. This eliminates the need for separate checks for uppercase and lowercase vowels, simplifying the logic. Now, let's examine the data structures used. First, we use a set for the vowels. This is ideal because it provides an average time complexity of 1 for membership checks, which is crucial when processing each character in the string. Second, we use a list to store non-vowel characters. Lists are efficient for incremental appending, allowing us to build the result dynamically with minimal overhead. To summarize the algorithm, the pseudocode is as follows. We define a function remove_vowels that takes an input string. Inside the function, we create a set of vowels and an empty list for the result. We then iterate through each character in the input string. If the character is not in the vowel set, it is added to the result list. Finally, we join the contents of the result list into a string and return it. This step-by-step process ensures clarity, efficiency, and correctness in removing vowels from any input string. Analyzing the complexity of the algorithm, the time complexity is O(n), where n represents the length of the input string. This is because we iterate through the string once, and each membership check in the vowels set takes O(1) time on average. The space complexity is also O(n). This arises from the need to store the result in a list, which, in the worst case, could contain all characters from the input string if no vowels are present. Let's walk through an example to illustrate how the algorithm works. Suppose the input is hello, world. First, we initialize the vowel set, containing both uppercase and lowercase vowels, and an empty list named result. Then we process each character in the string one by one. The character H is not a vowel, so we append it to result, making the list H. The next character, E, is a vowel, so we skip it. The following character, L, is not a vowel, so we append it, resulting in H, L. We repeat this process for each character, skipping vowels like O and appending non-vowel characters like comma or W. Continuing the example, after processing the space character, which is not a vowel, it is appended to the result list. Next, the character W is processed and, since it is not a vowel, it is added to the list as well. The vowel O is encountered and skipped. Then R, L, and D are processed in sequence, all of which are non-vowels, and they are appended to the result list. Finally, the exclamation point is also appended, as it is not a vowel. At the end of the iteration, the result list contains the characters H, L, L, W, R, L, D, exclamation point. These characters are then joined to form the output string HIL, world. This string is returned as the final result. The algorithm successfully removes all vowels from the input while preserving the order and integrity of non-vowel characters. This example demonstrates the efficiency and clarity of the approach, making it robust and adaptable for various input cases. This Python solution removes vowels from a string by iterating through each character and filtering out vowels. Here's how it works step by step. 1. Define the vowel set. We create a set of lowercase vowels, a, e, I, o, u, for quick lookup. Using a set ensures that membership checks, i.e., which are not in vowels, are efficient, with an average time complexity of O(1). 2. Initialize the result list. We declare an empty list result to store the characters of the input string that are not vowels. Using a list allows us to efficiently append non-vowel characters during iteration. 3. Iterate through the string. Using a for loop, we iterate over each character of the input string S. For each character, if it is not in the vowel set, we append it to the result list. This filters out all vowels while preserving the order of non-vowel characters. For join and return the result, once the loop completes, the result list contains all the non-vowel characters of the original string. We use the join method to concatenate these characters into a single string, which is returned as the final output. ### edge case is handled. Empty string. If the input string is empty, the loop does not execute, and the function directly returns an empty string. Strings without vowels. If the string contains no vowels, all characters are appended to the result list, and the output matches the input. Strings with only vowels. If the string contains only vowels, no characters are appended to the result list, and the function returns an empty string. ### complexity analysis. Time complexity, O(n), where n is the length of the input string. This is because we iterate through the string once, and set lookups are O(1) on average. Space complexity, O(n), for the result list, which stores the non-vowel characters. This is the Java implementation for LeetCode problem number 1119, remove vowels from a string. It mirrors the Python logic and uses a string builder to efficiently construct the result string. A string is used to store vowels for quick lookup with the index of method. The solution iterates through each character of the input string, checks if it's a vowel, and appends it to the result only if it is not a vowel. This approach ensures clarity and efficiency. To solve the problem of removing vowels from a string, we start with an example where the input is LeetCode. First, we initialize two key variables. The variable vowels is a set containing all the lowercase vowels, a, e, I, o, and u. Using a set allows us to perform quick O(1) lookups to check whether a character is a vowel. Next, we initialize an empty list called result, which will be used to store the characters from the input string that are not vowels. Now, we begin iterating through each character in the string LeetCode. In the first iteration, the current character is L. Since L is not in the vowel set, it is appended to the result list, which now contains L. In the second iteration, the current character is E. This time, E is found in the vowel set, so we skip adding it to result and proceed to the next character. Similarly, in the third iteration, the current character is again E, which is also a vowel, so we skip it as well. At this point, the result list remains L. Continuing with the string LeetCode, we proceed to the fourth iteration where the current character is T. Since T is not in the vowel set, it is appended to the result list, which now becomes L, T. In the fifth iteration, the current character is C. As C is also not a vowel, it is added to result, resulting in L, T, C. In the sixth iteration, the current character is O. This time, O is found in the vowel set, so we skip it and do not add it to result. The seventh iteration brings us to the character D. Since D is not a vowel, it is appended to the result list, making it L, T, C, D. Finally, in the eighth iteration, the current character is E. As E is a vowel, we skip it, leaving the result list unchanged at L, T, C, D. Once we have finished iterating through the string, the result list contains all the non-vowel characters L, T, C, D. To produce the final output, we join the characters in the result list into a single string using the join method. This gives us the string LTCD, which is the input string LeetCode with all vowels removed. Moving on to another example, let's take the input string hello. As before, we initialize the vowel set and an empty result list. We begin iterating through the string. In the first iteration, the current character is H. Since H is not in the vowel set, it is added to the result list, which becomes H. In the second iteration, the current character is E. As E is a vowel, we skip it and proceed to the next character, leaving the result list as H. Continuing with the string hello, we now process the third iteration where the current character is L. Since L is not a vowel, it is appended to the result list, which now becomes H, L. In the fourth iteration, the current character is again L. As before, L is not in the vowel set, so we add it to result, updating the list to H, L, L. In the fifth and final iteration, the current character is O. As O is a vowel, we skip it, and the result list remains H, L, L. After completing the iteration, we join the characters in the result list into a string. Using the join method, we get HIL, which is the input string hello with all vowels removed. This gives us the output HIL. Now, let's consider a third example where the input string is AIOU, a string that consists entirely of vowels. As always, we begin by initializing the vowel set and an empty result list. Starting the iteration, the first character in the string is A. Since it is found in the vowel set, we skip it and move to the next character without modifying the result list, which remains empty. In the second iteration, the current character is E. As E is also a vowel, we skip it as well, leaving the result list unchanged. In the third iteration, the character is I. Once again, since I is in the vowel set, we skip it, keeping result as an empty list. Continuing with the string AEIOU, we proceed to the fourth iteration where the current character is O. Since O is a vowel, we skip it and move to the next character, leaving the result list empty. Finally, in the fifth iteration, the character is U. As U is also a vowel, we skip it as well. At this point, we have iterated through the entire string, and the result list is still empty because every character in the input string was a vowel. To generate the output, we join the result list into a string. Since the result list is empty, the join method produces an empty string as the output. This means the input string AEIOU with all vowels removed results in an empty string, which is the final output. In this solution, we analyze the time complexity by breaking it into distinct steps. First, the initialization of the vowel set, which contains the characters of E, I, O, and U. This step is independent of the size of the input string S, so it takes constant time, O1. Next, we iterate through the string S using a for loop. The loop executes once for each of the n characters in the string. Within the loop, we perform two primary operations, checking if the current character is in the vowel set and appending non-vowel characters to the result list. Both of these actions are O1, because set lookups and list appends are constant time operations on average. Since these O(1) operations are performed for each of the n characters, the total contribution of the loop is O(n). Finally, after the loop, we use the join method to combine the characters in the result list into a single string. This operation processes all n characters in the list and thus takes O(n) time. Altogether, we have three steps: O(1) for initialization, O(n) for the loop, and O(n) for joining, which results in an overall time complexity of O(n). When we combine the time complexities of all the steps, the total becomes O(1) for the initialization of the vowel set, O(n) for iterating through the string, and another O(n) for the join operation. Adding these together, we arrive at an overall time complexity of O(n). Moving on to space complexity, the solution requires additional memory for three components. First, the vowel set, which is fixed in size and holds only 5 characters, so it takes O(1) space. Second, the result list, which stores all non-vowel characters from the input string. In the worst case, if the string contains no vowels, the list will store all n characters, requiring O(n) space. Third, the final output string generated by the join method will also require up to O(n) space in the worst case. Therefore, the overall space complexity is the sum of O(1) for the vowel set, O(n) for the result list, and O(n) for the output string, leading to a total space complexity of O(n). To understand why this solution is efficient, let's compare it with a naive approach. A less optimized method might involve repeatedly removing vowels from the string using operations like s.replace, or manually creating a new string character by character. These approaches would require multiple traversals of the string, leading to a time complexity of O(n) squared, due to repeated processing of the string. In contrast, the optimized approach used here processes the string in a single pass and uses efficient set lookups to determine if a character is a vowel. This avoids redundant traversals and achieves a time complexity of O(n). Now, considering the best, average, and worst-case scenarios, the solution remains consistent. Regardless of the content of the string, whether it contains no vowels, a random mixture of vowels and consonants, or is entirely made up of vowels, the loop still processes each character exactly once, and all operations within the loop are constant time. Thus, the time complexity is O(n) in all cases. Finally, let's confirm the time complexity mathematically. The for loop executes exactly n times, once for each character in the string. Within the loop, the set lookup to check if a character is a vowel is O(1), and appending to the result list is also O(1). Together, these operations are performed n times, contributing O(n) to the total time complexity. After the loop, the join operation combines the characters in the result list into a single string, which takes an additional O(n). Adding these together, the total time complexity is O(n) plus O(n), which simplifies to O(n). Similarly, for space complexity, the largest contributors are the result list and the output string, each of which can grow to a maximum size of n in the worst case. Since the vowel set is fixed in size, its space usage remains O(1). Combining these, the overall space complexity is O(n), driven by the size of the result list and the output string. This confirms that the solution is both time and space efficient, with O(n) complexity in both aspects. When solving this problem, there are several common mistakes to watch out for. First, it's easy to forget about uppercase vowels like a and e. If your solution only checks for lowercase vowels, it will miss some cases. To handle this, you can normalize the case of the string or explicitly check for both uppercase and lowercase vowels. Next, using str.replace in a loop can be very inefficient because each call creates a new string, leading to O(n*v) time complexity, where n is the string's length and v is the number of vowels. Instead, aim for a solution that processes the string in a single pass. Additionally, remember that strings are immutable in languages like Python, so modifying them repeatedly can lead to poor performance. A better approach is to use a list or string builder for efficient concatenation. Also, don't overlook edge cases. Test your solution with inputs like an empty string, a string without vowels, or one made entirely of vowels to ensure robustness. Finally, avoid overcomplicating your solution. For example, using a hash map to store vowels adds unnecessary complexity when a simple set or direct comparison will work just as well. In interviews, efficiency is key. Interviewers typically prefer solutions that run in O(n) time, as this demonstrates your ability to write optimized code. Be ready to explain the trade-offs between a brute force approach and a more efficient one. Edge cases are also important to discuss. Make sure to highlight how your solution handles scenarios like empty strings, special characters, or mixed case inputs. Another critical aspect is readability. A clean, straightforward solution with meaningful variable names is often more impressive than an over-engineered one. Lastly, be prepared to discuss trade-offs in your approach. For example, a solution that uses a set for faster membership checks might consume more memory compared to a simple loop-based approach. If time allows, you can also connect this problem to similar ones, such as reversing vowels in a string, comparing strings with backspaces, or validating palindromes, to demonstrate your breadth of knowledge. Now let's explore some alternative approaches and their trade-offs. Using a set for vowel lookup is a common technique since it allows O(1) membership checks, making it faster than checking a list. However, this approach does require additional memory to store the set. Another option is a regex-based solution, which can simplify the code significantly. But keep in mind that regular expressions may introduce overhead, making this method slower for very large inputs. A more efficient and memory-friendly approach involves constructing the result using a list. By appending non-vowel characters to a list and joining them at the end, you achieve O(n) time complexity while avoiding the overhead of repeated string concatenation. Finally, for problems with additional constraints, such as reversing vowels, a two-pointer technique can be a great choice for in-place operations. This method is especially useful when minimizing space usage is a priority. Great job! To wrap up, we reviewed the key aspects of the problem, including the algorithm, time and space complexity, and takeaways. Keep practicing these types of string manipulation problems to strengthen your skills. Thanks for watching, and don't forget to like and subscribe for more coding solutions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!